Welcome everyone. My name is Vijendra Kumar Gupta and I am a PhD student in chemical engineering at IIT Kanpur. Today I am presenting seminar on the topic of designing of shell and tube heat exchanger. Before discussing the designing of shell and tube heat exchangers, first we should know about the heat exchangers and their following types. So a heat exchanger is a system used to transfer heat between the two or more fluids. Heat exchangers are used in both cooling and heating processes. The fluids may be separated by a solid wall to prevent mixing, or they may be in a direct contact. They are widely used in space heating, refrigerations, air conditioning, power stations, chemical plants, petroleum refineries, natural gas processing, etc. The classical example of a heat exchanger is found in an internal combustion engine, in which a circulating fluid known as heat coolant flows through radiator coil and air flows past the coils, which cools the coolant and heats the incoming air. So, based on the applications, the heat exchangers are of various types, but there are mainly four types under which they can categorize. So, first is double pipe heat exchangers. So, double pipe heat exchangers are the simplest exchangers used in industries. On one hand, these heat exchangers are very cheap for both designing and maintenance, making them a good choice for small industries. On the other hand, their low efficiencies, coupled with the high space occupied in large scales, has led modern industries to use more efficient heat exchangers like shell and tube plate exchangers. However, since double pipe heat exchangers are very simple, they are used to teach heat exchanger designing basics to students as the fundamental rule for all heat exchangers are the same. Second one is shell and tube heat exchangers. They are consist of a series of tubes which contain fluids that must be either heated or cooled. A second fluid runs over the tubes that are being heated or cooled so that it can either provide the heat or absorb the heat required. The main constituents of this type of heat exchanger seems to be tube box, shell, and front, rear end headers and baffles. The baffles are used to support the tubes, direct the fluid flow through the tubes in an approximately natural manner, and maximize the turbulence of the shell fluid. There is various kinds of baffles, and the choice of baffle form, spacing, and the geometry depending on the allowable flow rate of the drop in shell inside force, and the need for tube support and the flow induced vibrations. Third one is plate and frame heat exchangers. Plate and frame heat exchangers contains an amount of thin shaped heat transfer plates bundled together. The gasket arrangement of each pair of plates provides two separate channel systems. Each pair of plate form a channel where the fluid can flow through. The pairs are attached by welding and bolting method. The following shows the component in the heat exchangers placed are produced in different depth, sizes, and corrugated shapes. There is different type of plate available which include plate and frame, plate and shell, and spiral plate heat exchangers. The distribution area guarantees the flow of fluid to the whole heat transfer surface. This helps to prevent stagnant area that can causes accumulation of unwanted material on solid surface. High flow turbulence between plates result in greater transfer of heat and decrease in pressure. And the final one is fin tube heat exchangers. They have tubes with extended outer surface area or fins to enhance the heat transfer rate from the additional area of fins. Fins tubes or tubes with extended outer surface area enhances the heat transfer rate by increasing the effective heat transfer area between the tubes and surrounding fluid. The fluid surrounding fin tubes may be processed fluid or air. So this one question may arises, that is why we need shell and tube heat exchangers. Since we are having the uh, double pipe heat exchangers which are easy to construct, so we are going to discuss double pipe heat exchanger, and we will come to know why we need shell and tube heat exchangers. So This is the schematic diagram of double pipe heat exchangers, and in which two cylinders of different radius are placed coaxially and streams are allowed to flow. If they are in parallel, that is, the one stream is going in that direction and other stream is also going in that direction, the flow to be known as the co-current flow. And if they are in opposite direction, that is, one fluid is in this direction and other fluid is in this direction, so they are known as counter flow. So in this heat exchangers we use adiabatic adiabatic operations for calculations, and the rate equation is given by uh, q dot is equals to m dot h cph thi minus the is equals to m dot c cpc tce minus tci, that is equals to ui ai delta t lmtd is equals to u naught a naught delta t lmtd, where THI and TE, TCE and TCI, they are the terminal temperatures of that processing streams, and Q dot is equals to have heat duty or heat load. M dot H or M dot C, they are known as the mass flow rate, and CPH and CPC, they are the physical properties, that is the specific heat of that hot and cold streams, and ui and u naught uo, they are the overall heat transfer coefficients based on inside and outside area respectively, and here ai and a naught, they are the inside and outside heat exchanging areas, that is, they are designing parameters. Note that delta t lmtd. So, what is the importance of LMTD in heat exchangers? LMTD is the logarithmic mean of temperature differences of the fluids at both the sides of heat exchangers. They are introduced due to the fact the temperature change that take place across the heat exchangers from the entrance to the exit is not linear. The use of LMTD arises straightforwardly from the analysis of a heat exchangers with constant flow rate and fluid thermal properties. So the limitations is this, that high area pipes are not feasible or economical for high heat duty because of the area. Hmm. So the other aspects are, that is, the pressure drop and the power required. So if we want higher heat transfer coefficient as or higher mass flow rate in direct and double pipe heat exchangers, so ultimately area going to be increased, so that we don't use a dphe in industries. If we want to increase heat transfer coefficient, so we have to increase the pumping cost, and that's why we have to install pump of high efficiency, that is mechanical efficiency. So it will lead to the increase to pumping cost in industries, that is not economical, as we can see from the formula, that is delta p delta p is equals to rho g hf, where hf is equals is head loss, and hf is equals to 4 times flv square by 2g deq, that is equivalent diameter, where v is equals to average velocity of the fluid. So v is equals to m dot by rho into area, where area is equals to cross sectional area of the pipe, and m dot is equals to mass flow rate. As we increase the mass flow rate, our our delta P, that is pressure drop, will also increase. In the same way, the power required is high in double pipe heat exchangers, as we can see P dot is equals to M dot G HF. In this, as M increases, the power required in double pipe heat exchangers will also increase. That's why we don't use DPHE, that is double pipe heat exchanger. So now coming to shell and tube heat exchangers. It is a class of heat exchanger designs. It is the most common type of heat exchanger in oil refineries and other large chemical processes, and is suited for high pressure applications. As the name implies, this type of heat exchanger consists of a shell, a large pressure vessel with a bundle of tubes inside it. One fluid runs through the tube and another fluid flows over the tubes, that is through the shell, to transfer the heat between the tube fluids. The set of tubes is called a tube bundle and may be imposed of several types of tubes, be plane, longitudinally, finned, etc. So the rate equations for this heat exchanger is given by the this expression that we see earlier, that is q dot, that is heat duty, is equals to the multiplication of the mass flow rate of hot uh, into the heat capacity of the hot stream into the temperature difference of the hot stream inside inlet and exit point, uh, is also equals to the heat gained by the cold stream. Here ui and u naught is equals to the overall heat transfer coefficient based on the tube and shell side area respectively, and ai and a naught is equals to the inside and outside heat exchanging areas. One thing we should notice in this is that flow in this heat exchanger, the flow is neither concurrent nor countercurrent. It is a multipass arrangement of the tubes inside this. So uh, we we use the correction factor term. So because of the multipass arrangement, the tube inside it, uh, we cannot evaluate the delta T LMTD. That's why we need to calculate the correction factor. And correction factor can be found by two parameters. First is temperature effectiveness, that is P, and second one is heat capacity ratio, that is R. Here, small t1 and small t2 are the temperature of the tube side stream, and small and capital T1 and capital T2 are the temperatures of shell side stream. So P, the temperature effectiveness, is defined as the ratio of temperature difference of tube side and maximum temperature difference, that is the difference of capital T1 minus small t1. In the same way, the heat capacity ratio is equals to the temperature difference of shell side and tube side. By getting P and R, we go through this chart to get correction factor F. Here, these are the contours that defines the R, and the x-axis defines P and y-axis defines F. For the double pipe heat exchangers, Fc is equals to 1, and for shell and tube heat exchangers, it is greater than 0 but less than equals to 1. For the designing purpose, correction factor should be greater than equals to zero point 0.8. When Fc is less than zero point 0.8, it indicates temperature cross in the heat exchangers. Further, we have to calculate AI, A naught, UI, and U naught. This rate law equation, as we've seen it earlier, so by comparing it with Fourier law, as we know that Q dot is equals to some delta T by summation R, where delta T is equals to the driving force in this case, driving force is equals to the temperature difference, and summation R is equals to the overall resistance. So by comparing these two, we get the summation R is equals to 1 by Ui Ai and 1 by U naught A naught, where Ai is equals to the inside surface area, and that is A naught, is equals to the outside area of the tube. So first we know about first we should know about the falling factor. The falling factor in these cases, that is Hi and Ho, represents the theoretical resistance to heat flow due to a buildup of a layer of dirt or other falling substances on the tube surface of the tube of the heat exchanger. So at steady state, we get the overall resistance, that is 1 by ui ai is equals to 1 by u naught a naught is equals to the resistance offered by the dirt factor inside the tube plus the resistance offered by the fluid plus the resistance offered by the dirt outside the tube. So by putting the values of ai and a naught in these expressions, we get 1 by ui is equals to this, and 1 by u naught is equals to this. So in the previous formula we have to calculate Hi and H naught. Rest terms are the literature value or the data that we generally know. So, but one thing should be noted in that formula is that Kf is equals to the thermal conductivity of the fluid, not material of the tube. Now the part is calculation of Hi. The Hi can be calculated by dimensionless number correlation. That is, Nusselt number of the tube side is a function of Reynolds number and Prandtl number. Uh, in this correlation, we have a parameter like rho f, mu f, Cp, Kf. These are the physical properties of the fluid that can be known by the literature. And di is the inner diameter of the tube. Nusselt number is equals to the Hi di by Kf. So the only parameter left is velocity of the fluid inside the tube, that is given by V bar is equals to the mass flow rate of the fluid in the tube side divided by rho f into number of tubes per passes into cross-sectional area. So by evaluating V bar, we get to know what is Hi, that is heat transfer coefficient of the tube side. So we have calculated Hi, that is tube side heat transfer coefficient. Now we have to determine the value of H naught, that is shell side heat transfer coefficient. To determine this, we generally use Kern's method. So before going through this method, few terminologies should be known. First one is tube pitch. Tube pitch is center to center distance between two adjacent tubes. In this diagram, uh, three tubes are generally are placed adjacently, and the center to center distance between two adjacent tubes is known as pitch, and clearance is gap between two adjacent tubes. So clearance is equals to the pitch minus the 2 times r naught, where R naught is equals to the outside diameter of the tube. So 2 times R naught is equals to the D. So basically C is equals to pitch minus D naught. For designing purpose, pitch is greater than 1.25 times D naught. In the same way, clearance should be greater than equals to 0.25 times D naught. Baffle cut. So the portion of baffle is removed for pass of the process flow stream of the shell side, and baffle spacing is distance between two adjacent baffles. So generally for designing, the baffle spacing is zero point 0.2 times of diameter of that shell. So it is apparent that higher heat transfer coefficient results when a liquid is maintained in a state of turbulence. To induce turbulence outside the tubes, it is customary to employ baffles, which causes the liquid to flow through the shell at right angles to the axis of the tubes. This causes considerable turbulence even when a small quantity of liquid flows through the shell. So the purpose of baffle is creating turbulence in shell side fluid. As the baffle spacing decreasing, the turbulency of that fluid will increase. That's why our heat transfer coefficient will also get increased, and as the time passes, the tube will get bent. So for not getting bent, we install baffles to provide supports to the tube. So number of baffles is equals to the length of heat exchanger divided by length of baffle spacing minus 1. So tube layout is characterized by included angle between the tubes. There are different types of tube layout, that are triangular pitch arrangement, square pitch arrangement, rotated square pitch arrangement, rotated triangular pitch arrangement. When tube pitch forms triangle, they are triangular pitch arrangement. Triangular pitch arrangement is used for the high heat transfer coefficient. It is better for heat transfer and surface area per unit length. So it provides a more compact arrangement, usually resulting in a smaller shell and the strongest header sheet for a specified shell side flow area.
This arrangement is preferred when the operating pressure difference between the two fluids is large. Second is square pitch arrangement. Tube pitch forms a square. In this, it is needed for mechanical cleaning. Uh, it is used when jet or mechanical cleaning is necessary on the shell side. In that case, a minimum cleaning lane of 1 by 4 inches provided. The square pitch is generally not used in the fixed header sheet design because cleaning is not feasible. Third is rotated square. In this, tube pitch forms rotated square in the same way. Next one is triangle pitch rotated. So tube pitch forms rotated triangular. Before going to determine shell side heat transfer coefficient, that is H naught, we should know about the equivalent diameter. The equivalent diameter is calculated along instead of across the long axis of the shell and therefore is taken as the 4 times the hydraulic radius, which is defined as the cross-sectional area divided by the wetted parameter. So for triangular pitch arrangement, equivalent diameter is equals to 4 times the area of that triangular or that equivalent triangle which is made, that is root 3 by 4 into the side square, and side in this case is pitch. So, and then root 3 by 4 pitch square minus the area of that part of the tube. So it is pi d naught square by 4, area of one tube divided by 2. So divided by wetted parameter, that is pi d naught by 2. In the same way, for the square pitch arrangement, equivalent diameter is equals to 4 times the area of that square, that is pt square, minus the area of the tube, area of the part of the tube, that is one sphere, that is one circle. So pi by 4 into d naught square divided by the wetted parameter, that is pi d naught. Now to determine the heat transfer coefficient at the shell side, we are coming back to this equation, that is dimensionless number correlation. In this, Nusselt number, that is H naught DEQ by KF, is a function of the Reynolds number and Prandtl number, except velocity at the shell side and equivalent diameter. All other parameter, that is rho f, mu f, cp, kf, these value can be found by the literature. So velocity of shell is equals velocity at the shell side is equals to the mass flow rate in shell side divided by uh, rho into cross-sectional flow area, and cross-sectional flow area can be calculated by the below formula, that is pt minus d naught, that is clearance into diameter of shell into baffle spacing divided by pitch. So by equating velocity at the shell side uh, to this Nusselt number H naught DEQ by KF, by putting the equivalent diameter from the previous results, we get HO. So now we get HI and HO, that is heat transfer coefficient on tube side and heat transfer coefficient of shell side. Now by putting these two terms in the original equation, that is 1 by Ui is equals to 1 by Hi plus the resistance offered by the fluid plus the Ri by Ro into Ho. So by solving, we get Ui and Uo, that is overall heat transfer coefficient based on inside area as well as based on outside area. So now the question is, what which is more efficient, a double pipe or a shell and tube heat exchanger? A shell and tube heat exchanger is more efficient as it can have multiple passes for the fluid to stay longer in contact with heating material. Longer contact time and higher heat exchange surface area allows greater help transfer rates, which is in accordance with Nusselt equation. But of course, it depends on the operation which type of heat exchanger must be used. In some cases, double pipe heat exchanger have been made long and tubular enough to allow the fluid to stay in contact longer and achieve a greater heat transfer with larger surface areas as well. But it would cost higher to achieve some heat transfer rates on a double pipe heat exchanger than a shell and tube one. So we are talking about the pressure drop. So main motive is how to lower pressure drop on the tube side of shell and tube heat exchanger. Tube side pressure drop can be lowered in following ways. First is increasing the shell diameter. That is, increasing the shell diameter increases the tube flow area due to increased number of tubes and thereby reduces tube flow velocity and hence reduces the tube side pressure drop. Further, it also means reduced tube length, which too leads to reduced pressure drop. Second one is increasing the tube diameter. Increase in the tube diameter reduces the tube velocity and thereby reduces pressure drop. However, tube diameters are standardized and standard outside diameter are limited. Further, tube outer diameter more than 1 inch is generally not desirable, as higher tube diameter means higher shell diameter to accommodate required number of tubes due to increased tube pitch, which in turn means higher cost. Third is increasing the nozzle size. If nozzles are too small in diameter, their diameter can be increased reasonably to lower the pressure drop. And using the shells in parallel. Multiple shell can be used in parallel so that tube side flow is split and flow velocity is reduced. Consequently, pressure drop is reduced. However, it increases the cost. And these are my references. And thank you for being part of this session.